Hello everyone, and welcome to the presentation of our WACV paper entitled Optimization Dense Visual Predictions through Multitask Coherence and Prioritization. Multitask learning is a field in computer vision that looks at optimizing multiple tasks simultaneously. This paradigm is particularly useful as it leads to faster inference time as opposed to having multiple single task networks, but it also reduces the memory complexity as a lot of shared parameters are used throughout multitask models. Finally, enhanced performance can be achieved as task relationships, if trained properly, can serve as a useful supervision signal for the network. However, multitask learning comes with a set of challenges evolving around its optimization. Firstly, during training, as a lot of parameters are shared throughout tasks, an aggregation of task gradient updates must be found. This can lead to destructive learning when gradients differ in direction or magnitudes. This phenomenon is also called negative transfer. Moreover, as we tackle dense visual tasks in this paper, complex pixel-wise cross-task relationships need to be learned if multitask performance can be leveraged to its full power. We identify these mappings as being firstly, prediction coherence, where pixel-wise coherence between task predictions is kept. For instance, where a ball is segmented, it would not make sense to have the distribution of flat surface normals along this object segment. Finally, we also define geometric coherence, where spatial relationships are preserved and consistent throughout task predictions. For example, high variations in depth values along a line in the image suggest the detection of an object boundary, which should be useful for semantic segmentation. Whilst prediction coherence has been investigated in previous research, geometric coherence is often overlooked. We see here an example where geometric coherence could be improved, where the table is geometrically well defined in the depth maps as a whole unique object, but segmentation fails to have smooth edges all underneath the table. In the attempt to alleviate these challenges, we propose a model entitled Multitask Coherence Prioritization. Our model overview can be seen on the right-hand side of this slide and shows how an initial prediction is obtained and then is fed all the task final image embeddings. The resulting features are then backtraced throughout the task-specific decoders to produce a final coherent task prediction which inherits from the useful help that auxiliary tasks are providing. Finally, in this paper, we introduce the loss prioritization scheme which balances task gradients in a dynamic and smooth manner. We now present our module architecture. Starting from left to right, our input image is processed by a mask to form a backbone, which serves as a feature extractor for all tasks. This results in the set of shared parameters R. Then, task-specific decoders takes the embedding R as input and will further tailor the image to serve the task at hand. The decoder blocks are shown in blue for semantic segmentation and green for depth estimation. The respective outputs are then concatenated through pyramid feature fusion to produce the representation XS and XD. At the end of each task decoder is attached a coherence fusion module presented at the top of this slide. CFMs aim at maintaining coherence for a particular task by diluting all the task image embeddings as auxiliary information. As shown in the diagram, auxiliary representations, shown in red, are processed by pixel-wise convolutions and later aggregated through concatenation. The resulting operation is then distilled through dot products and later processed by convolutions with the main task representations, shown in blue. Furthermore, the minimization of the cosine distance between the two set of features is applied to the overall objective to further maintain geometric coherence between tasks. The CFM output is then backtraced throughout the task-specific decoders through spatial refinement modules. These modules further improve both types of coherence defined earlier by concatenating intermediate decoder representations with the CFM. The concatenation is then processed independently to produce the output of the next CRM, and so on, as shown in the diagram. Alternatively, inspired by the work reference at the bottom right of this slide, we keep intermediate predictions of the decoders and add it to the overall loss to improve the discriminative power of our task branch. Finally, the final prediction is obtained through the last CRM. The final representation is more geometrically coherent, as shown in this example, where the initial representation lacks geometric information about the wall shelving unit. However, thanks to the use of the depth map information for this image in this prediction for refinement procedure, the final output segmentates the shelves in a more fine-grained way. We now focus on our loss prioritization scheme. Traditionally, multitask learning models minimize the following equation. This equation represents the weighted sum of task losses, where W's are weights applied to their task respective loss L. Generally, there are two options as for the choice of these weights. They can be either set as 1 over the number of tasks, resulting in equal weighting for all tasks. However, this is not desirable as tasks do not evolve at the same pace. Some losses might simply take over others. Therefore, previous research has demonstrated the advantage of projecting the loss scalars onto the logarithmic scale as shown in this equation. The second option is to manually choose the weights based on experiments. This is not desirable either, as this technique requires a lot of trial and error. Instead, task weights should ideally adapt dynamically throughout training, being able to focus on the more difficult tasks at a specific time during optimization. We therefore follow this paradigm introduced by previous research and extend it to user history h of epochs, as shown in this equation. Particularly, the nominator represents the evolution of a given task I over a history h of epochs, while the denominator represents the evolution of the overall progress of the model over the same history h. We then adopt this paradigm and summarize our minimization objective in this final equation. As experiments tend to show a fast convergence of the task weights, we choose to constrain our objective to spread the weights around their mean, controlled by a hyperparameter kappa, as shown here. To conclude, our work demonstrates the effectiveness of not only projecting losses onto a logarithmic scale, but also dynamically adjusting weights, constrained by a spread parameter. Now presenting the results, we show some visualizations of the refined predictions produced by our model. We show that although still some artifacts persist in the predictions, we show for the semantic segmentation and depth estimation tasks that geometric coherence is indeed achieved between predictions. We can notice that precision along edges is better, although some groups of pixels are still being misclassified by the segmentation task, for instance. We present in this slide the quantitative metrics obtained by our model on the NYU-DV2 dataset. Firstly, Table 1 shows that we outperform single-task versions of our model, showing the power of leveraging multiple tasks simultaneously. Secondly, Table 1 also demonstrates that our solution achieves multitask state-of-the-art results on semantic segmentation and depth estimations, whilst being competitive on surface normals estimation. On the other hand, Table 4 showcases the effectiveness of combining log smoothing and loss prioritization to our MTL objective. Indeed, the ablation of either of these elements reduces the performance for all tasks, whilst their combination leads to our state-of-the-art performance. On another note, Table 4 also proves the inefficiency of the equal weighting scheme for the reasons explained earlier. Thank you for listening. Feel free to have a look at our full paper as well as our code. We apologize for the current unavailability of our code due to a system fault. We aim to publish our code as soon as possible to enable the reproducibility of our results on both the NYU-DV2 and Pascal dataset. See you soon at WACV 2025 in Arizona.